Our entire world runs on wireless. Everything from the phone in your pocket to the smart devices that are popping up all over our cities, it's all built on this invisible web of connections. But have you ever stopped to think about how you design something so gigantic and complicated that you can't even see it? Well, today we're going to pull back the curtain and explore the incredible science of modeling our wireless world, how we design and perfect these massive networks in a virtual space before a single real-world signal is ever sent.
Really think about that question. We're not just talking about phones anymore. We're talking about networks that have to support self-driving cars, remote surgery, entire smart farms, billions of things. You can't just build it and hope it works. The cost, the complexity, it's just staggering. So with stakes this high, where do you even start?
Well, you start by running smack into what engineers call the wireless wall. And trust me, it's a massive set of challenges that stands between the networks we have today and the truly connected future we've been promised.
Yeah, this image really captures it, doesn't it? 5G isn't just about getting faster movie downloads on your phone, it's a complete paradigm shift. We're talking about building the literal backbone for our most critical systems, and the architecture you need to pull that off with all its layers of towers, vehicles, and data centers, it is just mind-bogglingly complex.
So let's break that complexity down into 4 huge challenges. First, there's the energy problem. How on earth do you power billions of new devices without completely draining our power grid? Then there's latency. How do you guarantee virtually zero lag for something as life or death as a self-driving car? And at the bottom, you've got the sheer density of it all. How do you handle the massive capacity demands and, at the same time, stop all those signals from turning into one big, chaotic mess of interference? You absolutely cannot guess your way through this. Trial and error just isn't an option at this scale.
So if building it in the real world first is a no-go, what do? Well, you build it in a virtual one. And that's the whole idea behind computational modeling.
Put simply, it's the science of creating a digital replica of a network. It's a way to experiment, to analyze, and to perfect the entire system right there on a computer. You get to find the best possible solutions to all those huge challenges before you ever spend a single dime on physical hardware.
This is probably the best way to think about it. Before a multi-billion-dollar jet ever gets off the ground, pilots spend thousands of hours in a flight simulator. That is exactly what's happening here. Engineers are test flying an entire 5G network. They're seeing how it holds up under stress, during a massive citywide event, or even in bad weather, all before a single piece of equipment is installed.
But, just like a mechanic needs more than just one wrench, a network modeler has a whole toolkit at their disposal. Let's take a look at the 3 main tools that they use to build these virtual worlds. First up, you've got mathematical modeling. This is about using pure math, things like optimization theory and queuing theory, to find the absolute perfect answer on paper. It helps answer questions like, what is the most efficient way to use power? Or what's the best way to manage data traffic to avoid digital traffic jams?
Think of it like the blueprint for a skyscraper. It isn't the building itself, of course, but it is the perfect, calculated plan that shows exactly how every single piece should fit together for maximum strength and efficiency. It gives you that ideal solution, at least in theory.
But a blueprint is just a plan, right? To really see how it's going to hold up in the real world, you have to build it. And that's where our second tool, simulation, comes into play. This is where engineers actually build a realistic, functioning replica of the network in software, so they can run countless experiments. Honestly, the best analogy here is a really advanced video game. It's a realistic, interactive world where you can play out thousands of what-if scenarios. What happens if 1 million people suddenly start streaming a live event? What if a solar flare messes with the signals? Simulation lets you see the network in action and find all those weird, unexpected behaviors you'd never see on a blueprint.
And that brings us to our third tool, which is the newest and, you could argue, the most powerful of them all, machine learning. Instead of being programmed with a bunch of rigid rules, ML models learn directly from data. They basically watch the network, find hidden patterns, and then teach themselves how to predict behavior and adapt on the fly.
This is kind of like having a self-taught genius managing your network. It just observes everything that's going on, learns all the little quirks, and then figures out how to make things better all on its own. It is absolutely fantastic for handling the chaotic, unpredictable nature of a real-world wireless network.
So when you lay it all out like this, it's pretty clear that each tool has its own job, right? Mathematical models give you that perfect optimal solution, but they often have to oversimplify things. Simulation is incredibly realistic, but man, it can be slow and super expensive computationally. And machine learning is brilliant at adapting to change, but it needs just massive amounts of data to learn, and sometimes its reasoning can be a bit of a black box. The real magic, as you've probably guessed, happens when you start combining them.
Okay, so this all sounds great in theory, but what does it actually look like in practice? Let's check out how these virtual models are creating some very, very real results out in the world. All right, let's start with a big one: energy consumption. The problem is simple. 5G is a power hog. So researchers used a type of mathematical model called convex optimization, which is just a super powerful way to find the most efficient solution to a problem with lots of constraints. The result? They designed a system that can intelligently dial power up or down based on real-time demand, which cuts down on energy waste dramatically without anyone noticing a drop in service. And hey, this isn't just about our phones and city networks. This kind of modeling is absolutely essential for the Internet of Things, especially when you're talking about remote places like in smart agriculture.
So get this, the challenge was how to keep these tiny little sensors alive for years on end without anyone having to go out and change their batteries in the middle of a giant field. By combining simulation with mathematical optimization, engineers designed a whole new way for these sensors to talk to each other. The impact was huge, a 35% reduction in energy use. That means the sensors last longer, which means lower costs and more sustainable farming. That's a huge win. So, these models have already completely reshaped our world, but this field is not standing still. Not even close. It's moving faster than ever. So, the question is, what's coming next?
What we're seeing right now is the rise of these hybrid models that mix and match the best of everything. But just around the corner, we're talking about digital twins. Perfect, live, virtual copies of our physical networks that let us do real-time fixes and optimizations. A little further out, advanced AI could give us fully autonomous self-driving networks. And beyond that, modeling is going to be the key that unlocks the next great frontier, the world of 6G.
And ultimately, this is why all this matters so much. Computational modeling isn't just some boring academic exercise. It is the essential, invisible architecture that's being built behind the scenes. It's the blueprint that is making our entire connected future possible.
It's a really powerful idea when you think about it. We've used this to build global communication networks and to make our farms more efficient, solving problems that really seemed impossible not that long ago. And it makes you wonder, what other complex systems are out there, waiting for us to understand them? What other incredible worlds are we going to build just by modeling them first?